Okay, so hello everyone. I'm Rohit Goel. I'm principal engineer with Expedia Group. First of all, I would like to thank Ignite Summit Forum to have us on here, and then thank you to all of you for joining in. So, we'll be doing a topic on lightning fast searches on Expedia using Apache Ignite. If we briefly talk about agenda, then will be introduction, then the why we needed the Apache Ignite in our business requirement, what was our heritage solution, then our new solution with Apache Ignite, of course, and then the how we executed it. We'll be sharing some of the best practices, and conclusion is more around what we achieved using Apache Ignite. So a brief introduction for the speakers, both of us here. We have Bhanu over here, who is also a principal engineer with in Expedia in flights team, and I'm Rohit. I'm also I share the same team as Bhanu. Then moving on to the business requirement. So if you see the flight searches on Expedia, we have millions of combinations possible for any routes. Consider Seattle to Las Vegas. You can have probably millions flights which can operate between different routes. And if you see the scale at which Expedia operates, we have thousands of TPS in our when the traffic is at peak level. Then if we talk about different studies which mentions that on every 100 milliseconds you have some user dropping off from your pages. So our flight search page used to be really latent, and we had this aim during the COVID cycles that we should be able to load our flight search result page in less than 2 seconds. So when we say less than 2 seconds, there were a were many large efforts across Expedia flights team to reduce the latency of our flight search result pages. One of them was on the caching. So if we see the Expedia is flight search is pretty high on the read system. So definitely we need caching, and uh, I'll share few requirement why and the deep dive. So if you see the departure flight page, you have first you have to choose a flight, and based upon what the user choose, based upon their session, and to provide the coherent experience, he or she will be moving to next page, wherein again they will be shown a curated result of flight lists, and they need to choose a flight. So I'm going to next. If you see, consider you have 90 flight solutions for departure and 80 flight solutions for arrival. So if you see in the in total, we have 7,200 combinations of flight possible. So based upon what a user is selecting on departure, we need to see what list we are showing on the arrival also. And having said that, popular routes like I mentioned on Seattle to Las Vegas, they can have 20,000 of possible solutions. So we need to store all these solutions into the into our cache. So this is our solution which we used to have using Cassandra. So whenever a client is making call to an hypothetical system called flight search service, it will be requesting either the departure page or arrival page. So we'll be going down level to our supply partners and to different GDSs and combine all the flight solutions. Then what we do is we do a three-step process. First, we uh, convert that to a fast info set and then compress it, and then store it into Cassandra. So the complete flight solution as a blob is stored into Cassandra, and we whenever we are getting the cache hit, we are fetching the whole flight combinations as a blob. Then the first step is we unzip the received information. Then we deserialize from fast info set to actual Java objects, and then again on that we try to find the flights for departure page or arrival page. So this is the three-step process which we used to do, and then we return the required response to the client. So in this heritage solution, these three steps used to take us 3 seconds. So Cassandra was pretty fast. We used to get the response, and if we talk about TP90, it was less than 250 ms always. And then these three steps, especially the unzipping and the deserializing part, it used to took almost more than 1.5 seconds, and this choose qualified flights would also take some time. So we thought of if we can if there is any improvement available. So instead of storing the complete flight information, we try to reduce all the duplicates. So we remove all the duplicates, which resulted into 20% betterment. But then again, we're not happy with that, so we tried to use cryo, and we tried to use different type of compression algorithms, etc. Instead of fast infoset, we used protos, but still we were able to get only 30% of the uh, latency gain. So we started looking into different other NoSQL DBs or better caching solution. One thing was especially the in memory part, and so we come across Ignite, which was an in-memory database only, and in-memory caching system based upon Jcache. So here we had more features, which was like first was binary object, then the affinity collocation, and the third one was remote computation. So if you see, our use cases were like we were getting a whole blob from Cassandra, and then deserializing and the complete blob, and then recompressing. So instead of all those things, we used remote computation, wherein instead of getting all the 20,000 flights into the service and then calculating the optimal solutions, we were calculating now all the optimal solutions on Ignite side, and we are heavily using binary objects wherein we can change the keys, values, etc. And so we have our data model looks like we have divided it into multiple cases, wherein instead of completely deserializing the whole flight combination, we deserialize only few fields which are required to identify a unique flight. So this is basically how our current solution look like. We have this JVM service, you can call it flight search service only. It is connecting to Ignite cluster via thick client. We put all the values in line by line, so row by row. If we have 20k combination, it will be having 20k rows in the Apache Ignite cluster. Then we just send the compute job over to a remote computation job executor, and then uh, it does all the deserialization whatever is required, all the filtering, and just return the specified finalized set of flight solution to this JVM service. Going to next slide. Over to you, Bhanu.
Thanks, Rohit. Hey, everyone. I'm Bhanu, and as Rohit mentioned, I work with him alongside the flights team to work on the solution that he just discussed. So, in our journey of revamping this whole flights caching infrastructure to move away from the previous data model and Cassandra-based solution to the new Ignite-based solution, let's take a look at some of the design choices that we considered before homing in on choosing Ignite. Some of the key things that we took a look at are your cache read and write patterns or the traffic patterns. The primary traffic that we get in Expedia is organic, but we have a lot of inorganic or bottish traffic as well, which sees a huge spike. So the solution should be able to cater to those spiky traffic as well. And then there are multiple solutions out there which limits or puts a size or limitation on the each entry that you can put in. We wanted to avoid those. The solution should provide a time to live, since our cache's flights data is extremely dynamic. Prices and availability change by the minute or by the second. So our caches are short-lived. Time to live was an important factor that we considered. And then there are hardware constraints like memory and network constraints. We primarily use AWS for all our deployments, and there are a lot of constraints on various EC2 machine sizes and the network bandwidth that can go in and out of that machine. So we took a look at both memory requirements and network constraints, so that the solution that we chose would have provided us both an opportunity to both vertically scale as well as scale horizontally. And on top of it, then we need to obviously account for some adequate buffer, so that if things go south, we have some breathing room. On the server side, the three main things that we finally implemented were the whole Cassandra server cluster was deployed on Amazon Web Services, AWS Cloud, EC2 instances, and we chose an appropriate size nodes based on our requirements so that we could, again, it was perfectly suitable for vertical as well as horizontal scaling. Instead of directly deploying Ignite binaries and managing it via various configuration solutions, what we did was we embedded the Ignite library within a Java service and bootstrapped it using Spring Boot. So what that provided us was Spring Boot provided us hierarchical environment-specific configurations, so we could have separate configurations for our prod clusters or test clusters or benchmarking clusters, etc. What this also enabled us was to quickly patch up some of the REST endpoints based on Swagger, etc., so that we could use them for debugging, housekeeping, and other stuff. It was much easier with embedding it within a Java service, because Java service was acting as a host to those endpoints. And it also allowed us to use out-of-the-box integrations like Vault, etc., for secrets keeping. So that was easier to use by embedding it within a Java service. And also at EG, we have a set template for services to deploy and release on cloud, wherein we have dedicated cloud formations which patches up services and bootstraps them on EC2 instances and provide a target group and an auto scaling group on top of that. So that was easier for us to do. And one of the other decisions that we took was the caches. We have multiple caches, and they are only owned by the server, and they are defined at the startup. Our clients only use those caches. They are not allowed to create those caches dynamically. Moving ahead, on the client side, the major decision that we had to take was between thin clients and thick clients. We chose thick clients because a lot of requirements that we needed out of this solution was primarily provided by thick clients. The Ignite version that we were using was 2.9.1, I think, which was the latest at the time of this implementation. The thick client supports continuous queries, which was very crucial for one of our use cases. We definitely needed full compute grid support because of the remote computations that we ran on the server, which was a major point in favor of Ignite to use the compute grid on the server side. And then having the topology aware and efficient collocation for clients as well provided the queries to be routed appropriately and minimize latency. Choosing thick clients also provided support for using near caches and data streaming, etc. We don't use them right now, but we could in future. Once our server and clients were set up, the other main design choice, or I would say the point to discussion, was how they would discover each other, both intra-cluster and between servers and clients. We started with a default TCP-based discovery using an ALB and ELB-based IP finders, but we quickly ran into multiple issues. I'll quickly touch upon some of them. For example, some of our clients who are behind were on, if you have worked on AWS, the containerization solution for AWS is ECS. So some of our clients were containerized on ECS, and they were using bridged mode. And what happens in the bridged mode is that the back port mapping doesn't happen correctly. So the servers are not able to find the clients, but the clients are able to find the servers. But since Ignite needs a two-way communication, so that didn't work out well. To use the ALB-based solution, that the way it inherently works is all the clients and servers go ahead and register them within target groups, and then when new clients and servers come up, they use AWS queries to AWS APIs to query the target group and then get a list of the healthy servers and clients and the other peers. AWS has a lot of rate limitations, so that didn't scale well, even with exponential backoffice, etc. The more amount of time it took for servers and clients to discover each other, the more issues we saw. And there were multiple other issues as well. So since the cluster grew to more than 100 nodes, and with the previous solution, the ALB-based one, they all arranged themselves within a ring. So even small messages, housekeeping messages, took a long time to traverse through the whole ring. Zookeeper to the rescue. We moved to a small Zookeeper 3-node cluster, and then it worked like a charm. The cluster arranged itself in a star-based topology, and the discovery was very, very seamless. To sum it all, in a pictorial manner. We had zookeeper instances there, which were front by Route 53s. So if some of the zookeeper instances were recycled behind the scenes, the Route 53s would remain the same, and the clients and servers would again query the DNS and get the latest entries. We have client ECS and EC2 machines here, which come and query the Route 53, get hold of Zookeeper instances, and then discover the other servers. So if new servers and new clients come up, they all discover each other using the Zookeeper-based discovery. To sum it all, in conclusion, if you remember some of the problems that Rohit mentioned, the time it took for the complete blob to be fetched and then deserialized and then returned back to the client. With Ignite, the cluster only took 10 ms, less than 10 ms to fetch the direct results. We ran a lot of remote computations on the server side so that the sorting and filtering, etc., is all, and the computation and the curated set of results is all done on the server side. And what clients get or what the flight or the JVM service gets is only that it's small set. So all the network bandwidth is saved, and you only get that curated set of data, which so the remote job was completed in 100 ms, and you got that very quickly. So the decompression and service processing was only a 40 ms. So overall, it only took around 150 ms for the 90th percentile of our search results. So in the original solution, it was the TP90, or the 90th percentile was around 3 seconds. We brought it down to 150 ms, which is around 95% improvement in latency, and was really a winner for us. All of these improvements, again, I would stress on, the primarily were due to the binary objects that Ignite supports. We were only able to deserialize the object part or the row part that we actually needed to. We didn't need to deserialize everything. That saved a lot of time. Remote computations on the server side saved a lot of time, both from a network bandwidth perspective and from a particularly due to collocation, etc. The servers were all using thick clients, so they were topology aware. They were sending the request to only those nodes that own the data. So all of this led to this huge improvement. And with that, I'd like to conclude the presentation and the talk. Thanks a lot. And I think we're ready for any Q&As that you guys might have. Thank you.
So thank you for that. Very good, interesting to hear. We've already got a question or two in the chat, so I'm going to jump to that and let's have a look. So we have a question from Bazidev Patil. How much data do you store in Ignite Cache, and how does large amounts of data affect performance? He says it has 40 million rows stored in Ignite Cache, and it grows as he also inserts the new data into the same cache. We continue to execute the select queries, and continuously cache will grow. Will it affect the performance? If so, does Apache Ignite indexes will be really helpful to achieve the performance in such a situation?
I can try that, right? So how much data did we really store in Ignite Cache? So we had a lot of nodes in the server cluster, more than 100 nodes. Each node had around 50 gigs of off-heap memory. We store the data only in cache. We don't use the third-party persistent or the native persistence that Ignite offers. With our page size, it really was around 10 to 15 million rows on each node max. That's maximum. So we didn't really see any performance issues since we had already horizontally scaled the cluster well. And since we don't use any of native persistence, then I guess we haven't taken a look at indexing as well. So, Rohit, if you want to add anything.
Yeah, just to add, just like Vasudev mentioned that 40 million rows, we do have at a time on the peak, we do have 40 million rows in one of our caches during the peak hours, but we have less than 1 hour of TTL for these caches. So our caches are not growing always. And one more thing is, as you mentioned on the indexing part, we most of our queries are only on the primary key and collocation key. So Ignite provides the indexing of that on those by default. So we do not need any special indexing, as we do not have any SQL like queries when we are calling Ignite.
Great. Okay, thank you. Next question from Jeremy McMillan. What are some legacy technologies performing these searches now? How does the new architecture based on Apache Ignite improve on them?
I can take this one. So, as we mentioned in the heritage solution, what we were representing is only on the caching part. When we have when we have fetched the result from all our partners and all our supply ruling and all those things are done. So, our legacy technology was Cassandra, wherein most of our changes are on the data model side in the Ignite. So we used to compress the whole result and deserialize it, and flight search responses are very huge. So with Ignite, we are storing them in a way so that we do not need to at first deserialize the complete thing. So let us say in binary object we have 6 fields. So we are compressing only 3 fields, which are complete response. The rest three we are not compressing, and there are very less fields which are unique, with which we are able to uniquely identify a flight. So it is mostly how the legacy technology versus the searches which we are doing on Ignite makes the caching fast.
Great. Okay. Next question. This is from Kashi Hasi. How did fetching from GDS delay your flight search?
All right. So to the listeners, GDSs are global distribution systems, or the third-party inventories. Expedia doesn't own much inventory. For a lot of inventory related to flights, etc., we rely on these third-party systems which contact other third-party systems to get the flight inventories and pricing and schedules. So we really rely on these third-party systems for our flight results, and these, since they are outside Expedia, they are not under our direct control around the latencies that they offer. Some of these calls to GDSs take a lot of time to display flight results. However, what's in our control is to at least display the results as fast as possible from our caches, and that's what we are trying to improve. So even the cache results were taking a lot of time earlier, but we have improved that a lot with Ignite.
Great. And then there's a last question about consistency of response time from Bill Friedman. So the question is, how much variance is there in query results depending on busy days versus slow days on the Expedia site? And is the 150 millisecond response time generally consistent?
Yeah, I would say since we have already accounted for the busy days to a cluster, some would say that the cluster might be a little over provisioned to account for these things. So the spikes do not really affect us that much if it's served from the cache. So a 150 ms response time, as I mentioned earlier, was a 90th percentile of a response. It's much better than that for the 50th percentile. So to the human eye, it's almost the same once it gets from the cache.
Great. Okay. Thank you. There's another question about the data model. So what changes did you make to your previous data model to make best use of Ignite?
Yeah, sure. I can take this one. So we used to have the complete flight search response, and for the record that can be in MBs. So no brainer, it was very performant to fetch a single entry for the complete flight search response from Cassandra, because it was really performant. But when we selected Ignite as our caching solution, we wanted to have minimum time on compression and deserialization. So at first we divided our tables into multiple parts. First was containing only the collocation keys, and the second table in Ignite is actually containing the data. And instead of storing the complete flight search blow we are storing single flight solutions, and we are storing whatever is required for we that is also divided into two parts. First one is which we need to compress, and the second one is which we do not need to compress, and we can uniquely identify a flight. So a data model at the end of the day is, at first we have multiple tables to represent the same data, and we are making heavy use of binary objects so that we can avoid unnecessary deserialization and compression. So that's the basic difference between Cassandra and Ignite to our data model.
Okay. We have another question now from Lokesh Pandaru. Cold starts, cache warm-ups. How did you manage to avoid them? If not, how long was it taken? Given the cache you have seemed to have well partitioned, or has the cache build-up always been incremental?
Yeah, so we generally don't face any cold starts or cache warm-up issues because of the use case. The caches or the rows are unique to a user. So before a user even starts to make a search on the site, we have some preemptive searches going in, and we make sure that to hydrate the cache really faster before the user actually goes ahead and makes a search. And so the cold starts didn't really hamper us. As you have, the second part is already assuming the cache buildup is always incremental, and we have been able to do complete cache replacements on the fly and changes to the server cluster on the fly without any downtimes, etc.
Great. Okay. And then related, next question. You mentioned that you have multiple caches, but how did you leverage the collocation in server-side compute jobs?
Yeah, so that's again one of the things that went in favor of Ignite while we were scavenging through the various solutions out there. So for the way the generally collocation works is we have all of our multiple caches we have defined an affinity key. All of them make use of that affinity key, and since we are using thick clients on the client side, they are all topology aware. They make use of the same affinity key to send the query directly to the node which owns the data, and that node again that runs the compute jobs makes use of that affinity key. Since all the cache data is for that key stored on that particular node only, it sorts, filters, does this thing, curates the data into a small set, and then just gives it back. So collocation is really central to how we achieve this perf improvements.
Great. Okay. So were there any other solutions that you explored? I mean, did you explore any other solutions seriously?
Yeah, so we had a look on basically Redis with its PubSub capability, and then the Hazelcast. It has these in-memory things, and has a bit advantage over the serialization and compression things. But as we mentioned, the binary object, server-side compute, and affinity collocation were the factors which forced us to use Ignite, and we are just mesmerized by how these things were supported out of the box in the Ignite. So we didn't spend much time after learning this concept of Ignite on other solutions.
Great. Okay, and I think we have one final question. No, there are two final questions. So we have a question here from Latha. Since you are using EC2, do you have auto scaling enabled? If yes, how do you handle the scale down process so that data loss will not occur?
Yeah, so
We are using EC2. Go ahead, Rohit.
Okay. So yeah, we are using EC2. We do have auto scaling enabled, and at first our cluster is a bit over provisioned, so we do not face much of the downscaling. Is the first thing, and as we have mentioned, our caches are incremental, and they do not have very large TTL per se. So it's fine even if we are losing a few machines and we are scaling down. We will be having those caches built up again. So and this is not this is kind of an L2 cache. It's not coming in the very much user flows which will affect on the search. It's just the latency which will be hit at the end of the day. So with the cluster, a bit of cluster over provisioning and incremental caching, we are we are fine with the losing few machines due to auto scaling.
Great. Okay. And then one last question, and this really is the last one, I think. It's a bit of an admin question. Is how much time did it take to set up this infrastructure in production?
I would say that this generally depends on the use case. So it all really depends on how mature is the product. So we set out a lot of time to do certain things, but as and when we went deep into Ignite, there were a lot of things that we got out of the box: the Spring Boot integrations, peer class loading, Ignite Zookeeper discovery modules, and etc. We didn't have to build any of that from scratch or worry about that. It was all already built out. So it didn't take long to be set up in production, but again, that depends on the use case. Since the product is mature and the documentation is good with good community support, I think with a little ramp up time, it's all done super smoothly.
Great. Excellent. Well, Rohit, Bhanu, thank you so much. Thank you for the talk. Thank you for a very detailed and engaged Q&A. Again, we hope you will stay and enjoy the rest of the day with us, and we look forward to having you back on future events.
Sure thing. Yep. Thanks for having us here, and thanks for all the great questions, and thanks, Jeremy, a lot.